For decades, cosmologists have stared at the night sky and told themselves a comforting story. The universe began as a smooth, uniform soup of gas and dark matter, and galaxies took shape slowly, patiently, through billions of years of gradual collisions and mergers. Nothing dramatic, nothing rushed, just the steady hand of gravity building complexity from chaos in a cosmos that plays by the same rules everywhere. That story is the backbone of our entire model of cosmic evolution. It is the reason our simulations match the large-scale web of galaxies we see today. It is why we sleep at night, believing we understand how structure formed after the Big Bang. But in the winter of 2022, the most powerful telescope humanity has ever launched turned its infrared eye toward the farthest reaches of space and returned images that made seasoned astronomers whisper the same desperate plea, "Please let this be a mistake." What they found were thousands of tiny crimson beacons glowing with impossible intensity in a universe that was barely 500 million years old. These specks, compact enough to fit inside the orbit of Neptune yet blazing brighter than entire modern galaxies, appeared everywhere JWS looked. They were so red-shifted that their light had traveled for more than 13 billion years, yet their spectra revealed mature stellar populations, heavy elements forged in stars, and in many cases, the unmistakable signature of supermassive black holes already weighing hundreds of millions of solar masses. In a cosmos that should still have been a toddler, these objects were already acting like fully grown adults. And here is the part that earned them the uneasy nickname that still sends shivers through the community. They should not exist. Not according to any equation we trust. Not according to any simulation run on the world's fastest supercomputers. If they are real, the rules that govern how stars ignite, how black holes accrete, and how galaxies assemble were broken from the very first chapter of cosmic history. Before we confront the data itself, we have to understand the bedrock assumption these objects annihilate. In the standard picture of galaxy formation, the first stars flicker into life around 100 million years after the Big Bang, tiny and metal poor. They die quickly, seeding the first black holes of perhaps a few hundred solar masses. Those seeds then grow slowly, swallowing gas at the Eddington limit, a strict speed limit set by radiation pressure pushing back against gravity. It takes billions of years for them to reach supermassive status. Meanwhile, galaxies themselves grow hierarchically. Small clumps merge into larger ones, gradually building disks and spirals. Every step is predictable, every timescale calibrated against the cosmic microwave background and the large-scale structure we see today. The equations are elegant, the predictions are crisp, and none of them allow for compact, ultra-luminous objects, with black holes already in the hundreds of millions of solar masses when the universe is still in diapers. To hunt for these first structures, JWST was built with instruments sensitive to the infrared wavelengths that red-shifted light from the early universe would stretch into. Its near-infrared camera and spectrograph were designed to pierce the veil of the cosmic dawn, revealing the faint glow of the first galaxies. When the first deep-field images arrived, astronomers expected to see hazy, irregular blobs still assembling themselves. Instead, they saw these razor-sharp red dots dominating the frames. Spectroscopic follow-up confirmed the redshifts, some at Z greater than 10, meaning we are looking at light emitted when the universe was less than 500 million years old. Luminosity measurements implied stellar masses, or black hole masses, that dwarfed every theoretical upper limit. The community's first reaction was instinctive disbelief. Surely the telescope's calibration was off. Surely the light was being magnified by unseen gravitational lenses. Surely dust was tricking the instruments into overestimating brightness. The hope that this was all an artifact ran so deep that entire papers were written, proposing subtle instrumental biases before anyone dared accept the data at face value. Yet the anomaly refused to vanish. When the next generation of observations arrived, using different filters and longer exposures, the red dots remained. When independent teams cross-checked with ground-based telescopes and later with refined JWST pipelines, the signal grew stronger. By 2024 and 2025, spectroscopic campaigns had mapped hundreds of them, revealing not just brightness but also velocity dispersions, emission lines from highly ionized gas, and in some cases, the clear kinematic signature of gas orbiting a central black hole at relativistic speeds. The mass estimates held, the redshifts held, and the timing held. These objects were not rare freaks. They appeared in every deep field, accounting for a significant fraction of all galaxies visible in the first billion years. Statistically, the probability that every single one was an artifact dropped below 1 in a million. The scientific community shifted from desperate hope that the data was wrong to the far more uncomfortable question: what is the universe trying to tell us? Whenever a finding threatens to overturn the textbook narrative of cosmic evolution, the first instinct is to blame our own backyard. The most prominent defense against these crimson anomalies was instrumental or environmental contamination. JWST observes through the haze of cosmic dust and the faint glow of foreground galaxies. If the subtraction algorithms were even slightly imperfect, scattered light from nearer objects could masquerade as distant beacons. Because the early universe is crowded with faint sources, any leakage in the data pipeline might artificially boost the apparent luminosity of compact sources. Another technical hurdle was the assumption of standard stellar populations in the models used to convert brightness to mass. If the first stars were radically different, hotter or more massive than anything we see today, the mass-to-light ratios could be miscalculated. Critics argued that we were applying modern templates to an alien epoch, forcing impossible conclusions from innocent data. Beyond the instruments, there was the look elsewhere effect. With billions of pixels across thousands of square degrees, any survey is bound to turn up statistical outliers. Perhaps these red dots were simply the extreme tail of a normal distribution, cherry-picked because they looked dramatic. Skeptics pointed out that if the telescope had instead highlighted unusually dim objects, we would have shrugged and moved on. The human brain, they reminded us, is wired to notice the impossible. Yet as 2025 and 2026 unfolded, the objections began to crumble. Multiple independent pipelines, using entirely different cleaning algorithms, still found the same population. Spectroscopic redshifts ruled out foreground contamination. Gravitational lensing models could not explain the sheer numbers or the consistent compactness. When the data from JWST's mid-infrared instrument and complementary observations from ALMA confirmed the presence of heavy elements and rapid star formation within these specks, the easy excuses evaporated. The anomalies were real, robust, and everywhere. The isolation argument that once comforted theorists also began to collapse. For years, skeptics could claim that if galaxy formation really happened this fast, we should see other signatures across the sky. By 2026, those signatures arrived in force. Massive galaxy clusters were caught assembling when the universe was less than 1 billion years old, their total mass already rivaling structures that should have taken twice as long to form. Ultra-bright blue monster galaxies appeared, compact and dust-free, yet shining with the luminosity of modern spirals. Supermassive black holes powering distant quasars were found to have grown to billions of solar masses far earlier than accretion physics allows. When you combine the red dots, the blue monsters, the early clusters, and the overmassive quasars, the statistical improbability under the standard model plummets toward zero. This is no longer a single strange population in one telescope's field of view. It is a coherent multi-messenger crisis, screaming that the early universe built structure with a speed and efficiency our equations cannot match. The reason this discovery is so deeply unsettling is that it does not exist in isolation. It joins a growing list of cracks in the standard cosmological framework. The same model that struggles to explain these crimson beacons is already wrestling with the Hubble tension, where different methods of measuring cosmic expansion disagree at high statistical significance. It is the same model that once confidently predicted slow, bottom-up growth, but now faces evidence of rapid top-down assembly across the cosmic dawn. If the universe could form mature, massive objects almost immediately after the Big Bang, then either dark matter behaves differently at high densities, or the seeds of black holes were far larger than we imagined, or the fundamental constants themselves shifted in the first few 100 million years. The Copernican assumption that our local physics is universal is not directly threatened, but the timeline we trusted absolutely is. We are forced to admit that the universe may have had a wildly different operating system during its first act. This forces us to confront the breakdown of hierarchical formation. If the red dots are real, both the slow merger paradigm and the Eddington-limited growth of black holes are technically wounded. Some theorists propose that we are seeing the signature of direct collapse black holes, born from pristine gas clouds collapsing straight into million solar mass objects without ever forming stars. Others invoke primordial black holes left over from the Big Bang itself, ready-made seeds that jump-started the process. But the most provocative frontier, emerging in 2025 and 2026, involves hypothetical dark stars, colossal objects powered not by nuclear fusion, but by the annihilation of dark matter particles in their cores. These monsters could grow to millions of solar masses, while remaining relatively cool and stable, eventually collapsing into the exact supermassive black holes we observe. Recent simulations show that dark stars could also explain the blue monsters, and even some of the red dots themselves, providing a single elegant mechanism that rewrites the entire first chapter of galaxy evolution without violating known physics. A newer and perhaps more radical idea gaining traction is the black hole star hybrid, an object in which a central black hole is cocooned by an enormous envelope of gas so dense that it mimics the behavior of a giant star. In this picture, the red color comes from the heavy dust and gas shroud, while the extreme brightness is powered by the black hole's accretion disk shining through. 2026 models demonstrate that such cocoons could form rapidly in the dense, turbulent environment of the early universe, solving the mass problem and the disappearance of the population after 1.5 billion years when the gas supply is exhausted. Whether the answer is dark stars, black hole stars, or an entirely new channel of rapid collapse, all these theories share one goal: to find a physical reason for the impossible without declaring the data false. They suggest that the early universe was not a gentle nursery, but a violent forge where exotic physics reigned for a brief cosmic moment. The crimson anomalies remain one of the most uncomfortable secrets in modern astronomy. For 4 years we have scrutinized them with every instrument at our disposal, hoping the signal would fade under higher resolution or better statistics. We moved from raw discovery images to deep spectroscopic maps, from luminosity arguments to kinematic modeling, and yet the objects persist. We have looked beyond their light into the chemical fingerprints of their stars, the motion of their gas, and the growth rate of their black holes. In almost every direction we have turned, we have found the same story of impossible maturity. As of 2026, we stand at a crossroads. The model that guided us for generations is clearly missing a fundamental chapter. We are seeing a universe that assembled itself with a speed and elegance our theories never anticipated. If these red dots are physical reality, then our fundamental understanding of cosmic dawn must be incomplete. The most conservative explanations invoke new formation channels that still fit within general relativity and the known particles. The more radical ones suggest that dark matter, or even the vacuum itself, behaved differently when the universe was young and hot. New missions like the Roman Space Telescope and upgraded ground-based arrays are already being tuned to chase these objects across wider fields and deeper redshifts. They will either deliver the definitive proof that our standard picture was simply too timid, or they will finally expose the subtle systematic that fooled us all. Until then, the little red dots remain a scar on our map of the early universe, a reminder that science is never settled, and that the cosmos is under no obligation to be simple or slow. We began this journey expecting to watch the universe grow up gradually, the way our models had always promised. Instead, we found a cosmos that leapt into maturity almost overnight, blazing with crimson beacons that mock every careful prediction. Whether those beacons are dark stars, black hole cocoons, or something still more exotic, they are pointing toward a new physics we are only beginning to glimpse. The universe is not the patient builder we imagined. It is faster, stranger, and far more creative than our equations allowed. And in that realization lies the deepest thrill of discovery. The moment when we realize the story is bigger than we ever dared dream, and we are lucky enough to be alive to read the next chapter. What will the next telescope reveal? The answer may rewrite everything we thought we knew about how the universe came to be.